Jambo class, welcome. I am your Mwalimu, and I am absolutely thrilled to have you join me for today's explainer on our Grade 9 Integrated Science syllabus. Today, we're going to look at something really exciting, waves. So sit up straight, get those notebooks ready, and let's dive into this together at a nice, steady pace. Here is our lesson plan for the day. We are keeping things very structured, so it's super easy for you to follow and remember for your exams. We're going to cover what is a wave, the types of waves, transverse and longitudinal shapes, wave characteristics, the all-important wave equation, and finally, a quick summary.
Okay, section 1. What exactly is a wave? Before we can do any calculations, we really need to understand what we're talking about here. A wave is, quite simply, a disturbance that moves through a medium. I want you to write that down slowly in your notebooks. A wave is a disturbance. That just means something is interrupted or moved from its resting position. And a medium? Well, that's just the material it travels through. It could be water, a piece of string, or even the very air around us. Section 2. Types of waves. Now that we know what a wave is, let's categorize them based on how they actually travel. It's absolutely crucial we contrast these two groups. First, we have electromagnetic waves. These are really special because they don't require a medium at all. No way! They can actually travel through an empty, silent vacuum. Think of a radio wave reaching us all the way here in Nairobi. It literally doesn't need water or air to get to your radio antenna. Then, on the other hand, we have mechanical waves. These absolutely require a material medium. For example, the sound wave of my voice right now, it needs the air to reach your ears. Section 3. Transverse and longitudinal waves. For the rest of our lesson, we're going to focus mostly on mechanical waves. Let's look at their specific shapes and movements. First, a quick point of clarification. If you flick a rope just once, that single, unrepeated disturbance is what we call a pulse. But if you keep flicking that rope regularly, up and down, you produce pulses that are repeated over and over. We call that continuous movement a periodic wave train. Let's look at the first shape, transverse waves. Imagine a rope moving up and down. The displacement is perpendicular to the direction the wave travels, so the wave moves forward, but the rope itself moves up and down. The highest point of that wave is called a crest, and the lowest point is called a trough. Now compare that to longitudinal waves. Think of a coiled spring. The particles of the medium vibrate parallel to the direction of movement. When the spring is pushed tightly together, that's called a compression. When it spreads apart, that's a rarefaction. Parallel movement is the real key to remember here. So let's put these two movements side by side to make it crystal clear. Transverse means perpendicular, with crests and troughs. Longitudinal means parallel, with compressions and rarefactions. If you memorize these differences right here, you're going to do very, very well when you're tested on this. Section 4. Characteristics of waves. Excellent work so far, class. Now we need to shift our focus just a little bit. Every wave has specific properties, and I must warn you, these terms are crucial because we need them for the mathematics coming up. Let's go through these very slowly. Please write them in your books. Speed, represented by the letter V, depends on the nature of the disturbance. Next is wavelength. That funny little symbol is a Greek letter called lambda. It's the distance between two successive points, like from one crest to the exact next crest, and it's measured in meters. Then we have frequency, F, which is the number of waves passing a given point in exactly 1 second, measured in hertz. Period, T, is the time it takes for one complete wave to pass, measured in seconds. And lastly, amplitude is the maximum displacement. Oh, and notice how frequency and period are closely connected, T equals 1 divided by F. Section 5, wave equation and practice. Okay, take a deep breath. We're going to put these characteristics together. Don't be afraid of the math. It's very simple and totally logical if we just follow the steps together, just like we would at the chalkboard. Step 1, speed, or V, is just distance over time, right? So the distance is our wavelength, lambda, divided by the time, which is our period, T. Step 2, we just learned that frequency, F, is equal to 1 divided by T. Step 3, because of that, we can substitute F right into the equation. So, speed equals frequency multiplied by wavelength. So what does this all mean? It brings us to this massive equation, V equals F times lambda. I want you to write this down inside a big, bold box in your notebook. It's the ultimate wave equation, and it literally unlocks so many answers in integrated science.
let's practice. Here is our first question. I'll read it slowly. A rope is displaced at a frequency of 3 Hz. If the distance between 2 successive crests of the wave train is 0.8 meters, calculate the speed. Before we look at the answer, ask yourself, what specific values have you been given here? Let's solve it together step by step. Step 1, we identify frequency. F is 3 Hz. Step 2, distance between successive crests is really just a fancy way of saying wavelength, or lambda, which is 0.8 meters. Step 3, we apply our formula V equals F times lambda. Step 4, we multiply 3 by 0.8, which gives us a speed of 2.4 meters per second. Wonderful effort. If you got that right in your head, you are doing absolutely great. Now, let's try a slightly harder challenge from our KICD materials. A wave travels at a velocity of 2 meters per second. Period is 0.20 seconds. Amplitude is 0.4 centimeters. Find the frequency and wavelength. This one actually has a small trick. Notice that we don't have our frequency yet. We've got to find it first.
Here's how we tackle it carefully. Step 1, find frequency. F equals 1 divided by our period, t. So 1 divided by 0.20 seconds gives us 5 Hertz. Step 2, write down the wave equation. V equals F times lambda. Step 3, we need to find wavelength, so we carefully rearrange the formula. Lambda equals V divided by F. Step 4, solve it. 2 divided by 5 equals 0.4 meters. Always remember to check your units class. Meters for wavelength, hertz for frequency, and meters per second for speed.
Section 6, lesson summary and next steps. You can let out a happy sigh now, my students. The hard mathematical work is officially done. You have done so well today. It's now time to wrap up our lesson.
Let's quickly recap these bullet points as your vital exam takeaways. First, waves transfer energy through a medium, which are mechanical waves, or through a vacuum, which are electromagnetic waves. Second, transverse waves have perpendicular movement with crests and troughs. Third, longitudinal waves have parallel movement with compressions and rarefactions. And finally, the mighty wave equation is V equals F times lambda. I speak with great pride when I say you have worked really hard to understand this today.
Looking forward to our next explainer session, we're going to explore even more characteristics of waves and see exactly how they apply to the beautiful world around us. So make sure you keep your notes safe, because your journey in integrated science is only just beginning.
I'll leave you with this final provocative thought. The next time you're walking home and you throw a small stone into a calm pond of water, don't just mindlessly watch the ripples. Ask yourself, like a true scientist, are you seeing a transverse or longitudinal wave? And using what we learned today, how fast do you think it's traveling? Thank you so much for learning with me today. Keep studying hard and stay curious.